Early menopause is a $56.7 billion problem for 17.2 million women in US, with a yearly cost of $429 million for 130,000 women. Every year it costs more than 100 plus deaths, type 2 diabetes, cardiovascular diseases, and dozens of dimensions. Now let us tell you how we calculated it. Hi, my name is Mark.
And my name is Elias.
And this is our ovarian aging value submission. To make presentation easy to follow, we'll walk you through the steps that we did one by one, starting from scratch and ending with the final deliverable of the website.
I'm going to start by presenting you the agent. And first of all, what is actually the goal of our agent? The goal is to extract as many risk metrics as possible from scientific literature, so we don't have to scour through thousands of papers and find the data for the numbers that Mark just told by ourselves. I believe that the best way of showcasing this agent is by actually running it. So now, while I explain to you how this agent works, the agent is going to extract risk metrics. The first thing that the agent is going to do is that it's going to take the disease of interest that me as a user I've specified, and it's going to create PubMed search queries based on that. Those search queries get then submitted to the PubMed API, and the agent gets back a huge pile of paper, abstracts, and other metadata. Then our agent goes through every single abstract one by one, deciding if the abstract is relevant or irrelevant for our disease of interest. For all the abstracts that are deemed relevant, the agent then tries to download the full text PDF. This works well for open access studies, but studies of closed access journals can't be accessed programmatically, so the agent creates a list of those studies that can't be accessed for us to manually download and then put in the pipe, so they are processed exactly the same as the automatically downloaded PDFs. Multiple Python libraries are then used to turn those PDFs into Markdown, and this Markdown is then fed into the LLM so it can extract relevant metadata. Then the agent judges the quality and trustworthiness of each paper based on the robust criteria as detailed by Whittings et al. 2016. Finally, the agent extracts the risk data, so the data that we were actually searching for, from the full text Markdown. In our final run, this agent ran for 5 hours and 22 minutes non-stop, read through 1,655 papers and extracted 584 risk metrics. If you could read one whole paper every minute, reading all those papers would still take you more than 24 hours. This agent represents a 30 times speed up over a normal researcher's, and this is assuming that this researcher never sleeps. This is how the final result then looks like, and I put the final CSV with all the 584 extracted risk metrics into our GitHub. I worked extremely hard to reduce hallucinations, so I dare you to click on any DOI in this CSV and check if the risk metrics are accurate, because I am convinced they are. We made all of our code and data open access under this repository, and there you can also find two videos. One where I walk through the whole code step by step, and the second one where I explain exactly how you can run this agent yourself. And now let's check what the agent extracted. As you can see here, the agent checked 42 metrics and found 23 interactions. Here in the terminal output, you can see exactly what the agent did, and this is the CSV that was created.
Now onto health methodology. There are 4 parts to it. First, choosing the risk values out of those 500 that Elias has provided us, mostly done manually, and making sure that the cohort constraints make sense, and the study quality is of course high, based on robust. And step number 2, finding annual incidence per 100,000 people for each of those diseases. 3, apply those 2 values and find the net effect. And 4, scale to yearly and US in total. Here I created a table that briefly summarizes some of our findings. Some of this data is more straightforward than others. So for instance, risk value is obvious, getting the net effect is obvious. Why do we scale to 130,000 people? This is because this is the number of women that enter menopause before 45 in US, and we'll make sure that our data represents the reality. Now let's talk about economic methodology. Once again, there are 4 parts to it. The first part is finding the annual direct cost per incident. And once again, so it's more of a witchcraft than science, but you always want to go for the best proxies, and we document that directly in our report. Second, we want to find also indirect costs. So if direct cost is something like medicaments and direct medical bills, indirect cost would be a loss of productivity, absenteeism, presenteeism. Then we take the net effect for 130,000 women and we multiply them by the annual direct and indirect cost to get the yearly cost, and you can perceive it as the yearly addressable market. What is important is that you have to take those costs then and scale them to 5 years, because this is a 5-year menopause delay, and we apply the present value for that. And lastly, you can scale that data to US in total, which is 17.2 million women altogether, and you can perceive that as total addressable market in US. Now let's talk a bit more specifics. Once again, we go in more detail for the report, but I just want to highlight one part, let's say, of all-cause mortality. What would be a direct cost of a dead man? There are no costs that apply to a dead man. That means we need to create a proxy for it. One useful proxy we found is the yearly cost in the last year of one's life. Then we want to calculate the yearly cost to 130,000 people. And then for this table, we take and scale our data to the 5 years and apply the present value of 3%. In general, there are 3 useful links for this project. First, the report with all our assumptions, sourcing, and exact values. Second, the code report that Elias talked about. And third, we proudly host menopauselater.com for our website as a final deliverable. The main idea is to tell a story. What is the problem that we're trying to solve? An instant impact that one can see, spreading the word about the information. And as a last word, we want to say thank you to Alexei, Nick, and Michael.
And we hope to see you next year.